Hello everyone, welcome to Mindspan Education. Last time this was the problem that was given to you, right? And we have two random variables x and y, and they are related like this. And if you plot this, then this is what you will get as a circle. And we have also told that we have the uniform joint PDF. That means we are interested in the probability of this region, and it is given that the joint PDF is uniformly distributed. That means each unit area will be equal probable, right? So that means the total volume under the joint PDF should integrate to 1, right? And if the joint PDF is uniformly distributed, right? So the the total volume should be 1, right? Then total volume means this area times the height, right? And height is what? Is nothing but this fx, this joint PDF, right? And what's the area of this? Pi r square, right? R is 1, radius is 1, so the total area will be pi, right? And the total volume should be 1. That means area, that is pi, into the height is this, right? So the joint PDF that you will get will be a constant, and that is why we are saying it is a uniformly distributed, right, per unit area. So this is what the joint PDF, it will be a constant number, that would be 1 divided by pi, right? And it will be 1 divided by pi within this range, right? And outside this the probabilities will be 0. Alright, now we have the joint PDF. Now we can find the marginal PDF of this random variable x and y, right? I will not do the calculation, I will just give you the instruction because it was supposed to be the homework problem, and you should solve this one, and I was expecting to have some comment regarding this problem, but anyhow, so how would you go further? So what's the marginal PDF of this random variable x? So for that you will have to integrate over y, right, to this joint PDF. So how you will find, what you will do, you will simply pick a specific x. Let's suppose let's take the value this here x, and if you see how this y is varying, this is how the y varies, right? And for each x, so for this particular x, this is how the y varies. For this particular x, this is how the y varies. For this particular x, this is how the y varies. Can you generalize this variation of y? Yes, given a specific value of x, yes, because we have this relation, right? So for this x, for in general x, the y will varies like this, right? So what will be the generic point of, or what will be the values at this for this x? So you can find from here, that would be plus minus root over 1 minus y square, right? For each values of whatever the x you fix, the y will vary from minus 1 minus x square to plus 1 minus x square, right? So the integral, for a fixed value of x, the y varies from minus 1 minus x square to plus root over 1 minus x square. right? And what's the joint PDF? That is 1 divided by pi, and here you will have the dy, right? Similarly, what you can do in order to find the marginal PDF of this random variable y, what you will do, you will now fix the value of y, pick any value of y, and see how the x varies. If you pick this value of y, if you pick this value of y, the x will varies like this. If you fix this value of y, the x will varies like this. And how you can get that? From this relation, right? So from this relation you can find that how x is getting varied, right? So from here x will be plus minus root over 1 minus y square, right? So the integral of this joint PDF with respect to the variable x, the x for a fixed value of y, the x will varies like this. That would be 1 minus root over 1 minus y square to 1 minus y square, right? And again that integral would be 1 minus y square and root over 1 minus y square 1 divided by pi dx, right? So I think I have already done that. So let me do the further calculation and let me complete this. So this will be 2 divided by pi root over 1 minus x square, right? So this is the marginal PDF of this random variable x, and we will have the marginal PDF of this random variable y, that is 2 divided by pi root over 1 minus y square. Once you have the joint PDF, then from this joint PDF we have found the marginal PDF of this random variable x and the marginal PDF of this random variable y. Alright, we will take more examples, but before that let me complete each and every concept of this joint PDF. Okay, now the next thing that we are going to look at is the joint CDF. We have already seen the CDF in case of a single random variable, right? So what is CDF? So CDF is nothing but probability such that random variable x takes the value less than equals to little x, right? This is what the CDF is, right? And if we have to denote, we denote like this. We have already seen this in case of a single random variable, right? And if we have to find this probability, how we can find? We just need to integrate from minus infinity to till this point, that is x, and this is the CDF, probability density function that we need to integrate from minus infinity to till this point, right? And if we want to get back this PDF from the CDF, then what we need to do? So we want to this, right? So what we will do, we will simply differentiate this. So this is the CDF, right? We will simply differentiate this with respect to x, and then we will have this PDF, right? So if we want to have again get back the PDF, what we will be doing is simply differentiating this CDF with respect to x. We have already seen in case of a single random variable. Now we have since two random variable, that is x and y, how we can define this cumulative distribution functions of two random variable. So that would be nothing but the probability such that random variable takes the value less than equals to little x, and at the same time random variable y takes the value that is less than equals to little y, right? So this is what the joint CDF, that is the joint cumulative distribution function, right? And this is how we can have the notation of this joint CDF. And if we are interested in finding this probability, how we can do that? Now since we have the two random variable, so probabilities will be distributed over this plane, right? And we are interested in finding such a way that this random variable x takes the value less than equals to little x. So this region, and random variable y takes the value less than equals to little y. So this, let's say this is little y. Let me less than little y, so this region, right? And for the x, this region, so common would be this region, right? We are interested in finding the probabilities of this region, right? How we can do that? The integral, the limit of this integral of this x will go from minus infinity to till this point, that is little x, and for the y, the integral will go from minus infinity to till this point, that is y, right? And we will be integrating this joint PDF, and let me use the different variable here. Why we are not going to use the again xy? Because in the CDF we are using these x and y, right? So this is different, right? So we have already used x and y, so let's use another random variable, another variables. We can call it as a dummy variable. So let's say this s and t. Alright, so this is what the joint cumulative distribution function is. Now if you want to get back this joint PDF from this joint CDF, how would you get that? So first of all, what you will do, you will differentiate this integral with respect to x, right? So this will be nothing but this integrand itself, right? Again, what you will do, again you will differentiate with respect to y, right? So you will get back this PDF. So you will differentiate this joint CDF twice. One, first you can integrate whatever you would like to do, maybe with respect to x or with respect to y, right? I think there is no doubt on these points, right? So we have, let's take an example. Let's suppose we have a uniform joint PDF and the probabilities are distributed over this unit area. So this is what we have given, and we are interested in finding what will be the joint CDF function. So as per the definition of the joint CDF function, this is nothing but the probability that random variable x takes less than equals to a certain value. At the same time, y takes the value that is less than equals to little y, right? So from this diagram, we are interested in finding the probability of this region, right? And how we can find this probability given this joint PDF? So we will be integrating from minus infinity to till this point x. So there is nothing till 0. So what we can do, we can integrate it from 0 to till this point x, and y integration will be from 0 to till this point y, and we have the joint PDF, that is 1 dx dy. So from here you can get xy. So this is how the CDF will look like of this PDF. And again, if you want to go back to the PDF, so if you have this CDF, how you can go back to the PDF? You just need to integrate this CDF first of all with respect to x, then again with respect to y. So overall you will get the 1, right? So differentiate this CDF first with respect to x, then with respect to y, right? So you will have ultimately 1, and that is what we have the PDF earlier that we have used or given in the problem, right? We will take more examples, but let me first of all finish all the concept regarding this joint PDF and CDF, then we will be taking more examples. In next video we will be looking at the conditional probability density function given another random variable. We have already looked at the conditional probability density function given an event, but next video we will be looking at given and condition over some another random variable. Okay, that is all in this video. Thank you so much.